Hello guys, nice to see you.
Good morning.
Hi.
Good afternoon.
Good afternoon, guys. Okay, let's maybe wait for a minute. More people will join. Hello, everyone. Yeah, nice to see you. Good. So let us probably shortly recall our previous discussion. So what we discussed on our previous meeting, it was definition of dimensions, a difference between dimensions and units, and some dimensional analysis, which either could be considered as some double check of your of correctness of the derived equation, or can also have this nice feature to derive some equations to describe certain physical quantities, which you don't know how to describe otherwise because there are not known or developed model for them. So with this approach of dimensional analysis, you can kind of predict the behavior, like in terms of mathematical equation of this certain physical process with accuracy of some constant. So that can be very helpful in terms of estimation of unknown physical quantities. So the key difference between, and probably the key feature of dimensions, who can remind, please, what exactly dimensions gives to a quantity? If you have just quantity, just number, that is, it doesn't possess any physical meaning. So once you assign dimension to a quantity, it becomes physical quantity, and then definitely it bears some physical meaning, which is already important in terms of physics. So we can compare between each other physical quantities with the same dimensions. And another important point to mention is that units can be different for physical quantity. However, dimension is the same and it defines the physical meaning of the quantity. Okay, so this is just short recall of our previous discussion, and today we can smoothly transit to the second topic in our schedule, which is vectors. So if you have any questions, you are welcome to interrupt me on the way and we can discuss this. And now we can, I believe, continue with introducing and discussion vectors. So as we mentioned earlier, there are different types of physical quantities. It could be a scalar quantity, like temperature, for instance. So it just has this numerical value, and that is sufficient enough for our needs. However, we can make an example of speed and velocity. So speed is also a scalar quantity, and it doesn't provide us the information on the direction of motion, just how fast it moves. However, velocity at the same time, it is already a vector, and besides, so it possesses two components. Its amplitude, which defines how fast the body is moving, and also direction. So it shows us the direction of its movement. Now we are going to talk more in details on vectors in general. So we are not going to go into describing some physical properties of these vectors. It's just introduction to the vector and introduction to the most common operations, mathematical operations, which can be carried out with vectors. And all this information is valuable because we definitely will have to do a lot with vectors along our course. So that's why it is defined in a separate topic, which should be considered at the beginning of this Physics 1 course. Let me change the camera so I can show you some visual content. And before we go to vectors, it makes sense to introduce a system of coordinates, at least two most common systems of coordinates. The most common one is just perpendicular system of coordinates, which has x and y axis. Then we have some body or some point on this plane defined by this system of coordinates, and its position is defined by projection towards the axis x and axis y. So this is coordinate y, this is coordinate x. So with these two coordinates, we can define clearly the position of this point on the system of coordinates. There is another system of coordinates which is commonly used in physics, and we will definitely work with it. It's so-called polar system of coordinates. And in this case, instead of providing y and x, like position of this point, its radius vector is provided. So in this case, it could be just r, just radius, because orientation of this radius is defined by angle theta. And so r is the equal to the length, like distance between the origin of the system of coordinate to the point, and theta is actually angle which defines the position of this body together with the radius. So there is a simple relationship between right angle system of coordinates and a polar system of coordinates, and you can actually see it from this figure. So we can write that x is equal to radius times cosine theta. We can consider this as right angle triangular, like A, B, and C. And based on this, we can write that x is equal to r times cosine theta, and y is equal to r sinus theta. Also, this angle theta can be defined by x and y. So we can write that tangent theta is equal to the ratio of y to x. And the radius r is actually the hypotenuse of this right triangular, and it can be defined as square root of x squared plus y squared. So these are the most important features of two most common systems of coordinates we are going to work with. And now we can smoothly go to vectors. Let's say, consider such classical example. We have point A and point B. Then we have some particle moving like this with such path from point A to point B. So the length of this curved line is called path. So it's path which body made to go from point A to point B. And this path is a scalar quantity. So it just defines how many meters or kilometers this body was going through while moving from point A to point B. And there is another quantity which is vector quantity and called displacement. So displacement, it's a vector which defines its orientation is defined by the line between 2 points, initial and final, and the amplitude of this vector is the distance, like shortest distance between these two points, A and B. So we already have a clear example between scalar and vector quantities. And as I mentioned earlier, vector is defined by orientation and by amplitude. So now let us consider which kind of operations we can perform with vectors. So let's say we have some vector A and vector B. So let's position the origin of vector B at the end of vector A. This is vector B. So now, if we want to have the sum of vectors, we can add them, A plus B. It will be equal to vector C, which goes from the origin of vector A and to the end of vector B. This is vector C. So this is the way how we add vectors. When we place beginning origin of the second vector, which we add to the end of the first vector. Here we need to highlight some other features. Let's say we have more vectors. So we have vector A, then vector B, and vector C, and vector D. So the sum of all these vectors, when we place them one after another. Beginning of next vector at the end of previous vector will be some vector, let's call it E, and the same story, vector E will be equal to the sum of all these vectors plus C plus D. Now, let's say we show this feature. Let's clean this vector here and move this vector B to the origin of vector A, more or less parallel. Here is vector B, and then this vector A we will draw from the end of vector B. We see that it doesn't matter what is the order of adding vectors. If we have, for instance, A plus B vector, it is equal to B vector plus A vector. So these are the features of adding vectors. And now we need to introduce some negative vector. Let's say we have vector A and vector minus A will be the same in amplitude and different, opposite in direction. So it means that if we add vector A with vector minus A, it will be equal to 0. So that gives us an opportunity to apply rules defined for adding vectors to subtracting vectors. So if we have A vector minus B vector, this could be considered as A vector plus minus B vector. Now, another important feature which is commonly used is multiplying vector by a scalar. So let's say we have 2 times A vector. So this will be equal to A vector plus A vector. And the orientation of this resulting vector will be the same as orientation of vector A. However, its amplitude will be twice increased. And we can do such operations, and they are quite common. So now we introduce unit vector, and then we'll start discussing in more practical way vector definition and also operations in vector, because now it is quite abstract approach. We have some vector in space, yeah, it has orientation, but it is very difficult to work with such vectors because we want to have vectors which are, we want to deal with components of vectors which are aligned along the axis, and that will help us like simplify a lot our quantitative analysis of some vectors. So in order to come to this point, we need to introduce unit vector. And unit vector, let's say I, has direction, but its amplitude is unity. So it is introduced with only one purpose. We can define direction to any scalar number. Let's say we have some number a, and if we multiply this by unit vector, we will get some vector, let's say a, which amplitude is equal to this scalar number a, and direction will be defined by unit vector I. So we can write that a is like parallel to vector I, and they have the same direction. Okay, let's go to another slide and introduce this some vector a, but already not in some abstract space, but in a given system of coordinates. So we have x axis and y, then we have vector a, and now we can find projections of this vector towards different axes. So here is projection of vector a on axis x. This is ax. And here is projection on axis y. So it will be ay. Now we want, in order to deal further quantitatively with this vector, we want to consider components of vector a, split it in two components because we have two axes, and deal with vectors which two vectors along axis x and y, which in sum can give us vector a. And in order to do that, we introduce here unit vector I. This is unit vector along axis x. Then we have here unit vector j. Along axis y. And based on this configuration and rules of adding vectors, we can write that vector a is equal to the sum of two vectors. And these two vectors are defined by the product of unit vector I and projection of vector a on the axis x. So it's I unit vector times ax, which is ax is just scalar number, plus unit vector j times projection of vector a towards the y-axis. So this is the form most commonly used in physics and to deal with vector quantities, because it is very convenient. So we have, instead of one vector which is arbitrarily oriented in space, we now deal with two vectors, but they are along the axis of our system of coordinates. And that makes a big difference. For instance, let us consider this rule of adding two vectors. Again, we have a system of coordinates, x, y. And let's say we have two vectors. So this is vector A. This is vector B. We have projections of each vector on respective axis. Now we have these components AX, and here from the origin we have BX. Now here we have AY, and this is BY. So now with introducing unit vectors I and j, we can write first the expression, quantity expression for each vector, which will be a vector is equal to I times AX plus j times AY, and the same for vector B will be I vector times BX plus j vector times BY. And the resultant vector C which will be the sum of two vectors A and B will be given in a very clear and simple equation. So we have just product of unit vector to the sum of projections of each vectors A and B on axis X will be AX plus BX plus J unit vector times the sum of projections of these two vectors A and B on axis Y. So it will be AY plus BY. As you see, it is very clear what you need to do in order to operate with vectors. You split it into components parallel to axis X and Y, and then you can easily add these vectors. If you need to subtract, then obviously here will be minus if you subtract vector B from vector A. So this is a convenient and very practical way to deal with vectors. So obviously we may have three-dimensional case. So far it was two-dimensional, and we can call it already multi-dimensional too, because the main transition, what happens between going from one-dimensional to two-dimensional, that we need to introduce these vector quantities. Once we introduce vector quantities, so we will discuss in more detail soon, starting from next week, motion in one dimension and motion in two dimensions. Once you introduce this vector quantity, then going to three dimensions, it technically the same process, you just add one more axis. So for instance, if we have three-dimensional system of coordinates, it is axis X, axis Y, and axis Z. And there is some point in this three dimension. Here is some vector. I mean, let's say just vector A. And obviously we have projection of this vector on each of the axes. So this will be AX, AZ, and a, y. And along each of these axes, we have unit vectors. It's I, here is unit vector j, and here is one more unit vector k. So once we have such system with provided unit like axis and unit vectors, we can define position and amplitude of this vector in three-dimensional space quite easily. It will be A is equal to AX times I plus AY plus times J and plus AZ times K unit vector. Similar to the two-dimensional case, that's why in future we will be mostly focusing on two-dimensional case just to make it less bulky in terms of equations, but the concept behind it is it's actually the same, so it doesn't make sense to just write too much. Now we can proceed further with rules for dealing with vectors, and makes sense to consider two options for multiplying vectors. By the way, is someone familiar with two options to multiply vectors, how they are called? So far, we were considering only adding and subtracting and multiplying vectors by scalar. However, it is also possible to multiply vectors. So there are two options. One is so-called scalar product or dot product of two vectors, and another is vector or cross product of two vectors. So let us consider these cases so we are familiar with this. We will start dealing with them a bit later, but definitely that is important in the scope of our course of mechanics. So let's say we have two vectors, again, A equal to AX times I vector plus AY times J vector. As I mentioned before, we will, but maybe for example here, to be more general, let us add also third component. Then we can say that we have the most general case. And vector B, the same, Bx, I, By, J, and Bz, K. So now let's start from the dot product. So dot product of two vectors, A times B, gives us the scalar number. So we will get the following. It will be AX times BX plus AY times BY plus AZ times BZ. As you see, we don't have here any unit vectors, so they kind of cancel out, and the amplitude of such, like the value of this scalar product of two vectors will be equal to amplitude of vector A times amplitude of vector B times cosinus alpha, and this alpha is the angle between two vectors. So this is a scalar product. For instance, maybe someone can give an example from mechanics. What is a good example of application of this scalar product?
Area.
You definitely should be familiar with that. Let's say we have some force exerted to body, and this body is moving because of this force and performs some displacement. So there are two vectors. Displacement is a vector, force is a vector. And then if we want to find the work done by this force for moving this body along this displacement vector, that is scalar product of two vectors, force and displacement. And then we eventually get work. Work is a scalar number, it's not a vector. So this case is a very good example of application of scalar product of two vectors. Yeah, exactly. A is equal to F times S as the displacement times cosinus alpha, which is the angle between force and displacement vectors. So here we wrote the same, but just in more general case, which is of course applicable to any situation. Now, let us consider another important product of vectors, which is called vector product or cross product. So in this case, usually this scalar products of two vectors, they are in such round parentheses, and this cross products are in some square brackets. So here we have vector A times vector B. And in this case, we get not a scalar number, but a vector. And this vector is actually oriented perpendicular to both vectors A and B. So we will focus on this a bit more in details when it comes to analyze some physical quantities related to the product of two vectors in mechanics, this orientation. But the key difference that we get instead of scalar, we get a vector. And where it comes from, so the most common and general approach to find the product of two vectors is to use vector product representation by matrix. So what we can write here, there is a matrix of 9 elements. So in the first row, we have I vector, J vector, K vector. And then we have A X, A Y, A Z, projections of vector A on all axis of the system of coordinate, and the same for vector B, Bx, By, and BZ. So now, according to the rules for multiplying two vectors in this matrix form, we can choose first I, then we exclude the column with I and this row with I, and we deal with these components. So it will be equal to I vector times, we go first diagonal from left top to right bottom. It will be AY times BZ minus another diagonal, which is from right top to left bottom, AZ times BY. So we are done with the X component of the resultant vector of cross product of two vectors. Then we need to proceed with Y component, which is defined in direction by unit vector J. Now we consider this vector J, and we exclude this row under vector J, and we have to deal now with these four elements of the matrix. So here it will be main first diagonal AX times AZ, so AX times BZ minus second diagonal AZ times BX. AZ times BX. So this is the projection of the resultant vector on axis Y. And finally, we have the last component. It is its projection on axis Z. So this is K. So we will deal now with these four components of our matrix. So first diagonal is AX times BY minus AY times BX. So that's it. Now we have this equation, which gives us the vector, which is cross product of two vectors A and B. So it's a bit bulkier than previous equations, but definitely very clear. And if you just keep in mind this vector like a matrix format of multiplying two vectors in as cross product, then it's very easy to recall how it's necessary to do calculations in order to get projections of each of this resultant cross product of two vectors on each system of coordinates. So in this case, we have most general case with three axes of in our system of coordinates. Obviously, if we have only two, that would be much easier and less bulky. But again, as I mentioned earlier, most of our examples will carry out in the system of coordinates with two axes, considering that it's already multi-dimensional space. Okay, so I guess we got already quite a lot of raw vector information, definitely not so applied knowledge which could be easily digested. But these are very important features of vectors which you guys need to know, or don't need to remember everything, but just need to know where to look and how to understand these operations with vectors. Because in future, we definitely will do plenty of tasks related with operations on vectors. So during this discussion, we had some like introduction of vector itself, defining what it is and why we need it, with some examples. And step by step, we considered this main mathematical operations with vectors, starting from simple general rules for adding vectors, subtracting vectors, introduced unit vector, which is very useful in terms of splitting vectors in two components or three components, depends how many axes of coordinates we have. When these component vectors are aligned in parallel to the axis of our system of coordinate, and that's why it helps us to deal in a very simple way with any mathematical operations with vectors. Doesn't matter either we have we add two vectors, subtract, or multiply. So that makes life much more structured and easy. And of course, you should practice this when possible and necessary to work with vectors. At this point, I think I would like to finish this introduction of vectors. And if you have questions, you're very welcome to ask. I believe that many things you already knew from before. However, it is not bad to repeat in any way, because some details can be forgotten, and maybe you also learned something new about vectors today, which you didn't know before. So you just need to be, so all of us should be on the same stage when we start going further. So we know that this minimum requirement is fulfilled, and you are familiar with the most important concepts, which will allow you to smoothly go through the course. Okay, guys, if we don't have any questions, I will not keep you longer. I wish you a good day and good end of the week. So have a good weekend and relaxed. Come back on Monday to our online discussions. Okay.
Thank you. Goodbye.
Thank you for attention.
Thank you. See you on Monday.
Bye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you.
Bye.
Bye. Bye.